Oh man, I've done this recording 10 times. Today we're going to take some notes. They're pretty brief notes, but last week just remember that we learned about the 3 different ways that heat was transferred. We learned about conduction, convection, and radiation. And today we're going to focus on the types of materials that transfer heat and electricity easily. So let's get into that. We know that some materials are called conductors, and we talked about this when we talked about electric circuits and how in order for the electricity to pass in a circuit, it needs to have, a source, like a power source, and then it needs to have an output device, which would be either the light bulb, the motor, or the buzzer, and then it would also need to have conductor wires, which would connect them all. So conductors are just materials that allow heat to pass through quickly. So when we're looking at conductive materials, they heat up really quick and they cool down really quick because of the material just allows that heat to move through. That was cute. So you don't have to write this example down because on the next page there's going to be a ton of examples. But when you have a metal pan placed on a heat source, it will get hot and it will conduct the heat to whatever is inside the pot. So that would be an example of a conductor transferring heat through conduction. So some examples of conductors, and you should see pretty quickly that most of the examples are a type of metal. Copper, platinum, aluminum, or if you're British, aluminium. Glass, metal, or I'm sorry, I said metal, but most of those are examples of metals. People and animals are good conductors of electricity and heat because we have a huge amount of water in our bodies, and this allows for the easy transfer of heat or electricity. And the opposite of a conductor is an insulator, and these are the types of materials that slow down the transfer of heat. It doesn't always stop the heat transfer altogether, but they do make it a lot slower. And different insulators have different degrees of slowing down. So an example would be like when you have oven mitts and you take like a pan of hot brownies out of the oven. If you're just reaching in, grabbing the pan of hot brownies and putting them down, you're not going to feel the heat come or transfer through the pan to your hand because you have those insulators on your hands. However, if you were to hold the tray of brownies for a longer period of time, you would start to feel the heat coming through because those little oven mitts are an insulator, but they're not stopping the heat altogether. They're just making the heat move more slowly. So that was cute too. Let's look at some examples. Any type of animal fat is an insulator. That's why a lot of Arctic animals have a thick layer of blubber surrounding their body. This layer of fat allows them to survive in an environment that is way too cold. And polar bears, for instance, are able to swim in freezing cold weather or water because they have that thick layer of fat. And that fat just traps their body heat and allows them to stay warmer. So here's some examples of insulators. Most of these are types of plastics or rubber or some combination of the two. Wool, wood, we already talked about animal fats, and styrofoam. Go. Okay, so we talked about how different materials have different degrees of being conductive or being an insulator. So it's kind of like on a scale. Not all materials will allow heat to transfer at the same rate. So if we're looking at a scale of good insulator to good conductor, as a good insulator, we have the styrofoam. And then right next to it, we have wood. Wood is still an insulator, but it's not as good of an insulator as styrofoam. So you're gonna be able to rank different materials based on how conductive they are. It's not all just like, oh, you are all insulators and you are all conductors. It's a scale of how quickly they allow heat to transfer. So this activity you're going to do in the Edpuzzle, you're going to pause, or it's going to pop up with questions just so you know what it's talking about. This is penny, this is a penny, this is wood, a styrofoam cup, silver, and I'm reading it because it looks blurry, paper, wool, soda can, frying pan, cork, trumpet, a gold ring, a rubber tire, wool gloves, a leaf, a brick wall, and a thermos. You're just going to identify these as conductor or insulator. So we're going to go into a totally different topic now, but I wanted to talk to you guys about what work is. Energy is the ability to do work. And we know that another definition of energy is the ability to make change. And that's what work is. Work is a type of energy, and it happens when you apply a force to an object and that object moves in response. So in order for work to be done, that object has to move over a distance in response to the force that you apply. So in this image down here, we see Home Slice down there pushing the barrel up a ramp, and the ramp is, or the barrel, guys, is a crate. Sorry. The crate is moving in response to the man's push, and it's moving in the direction of the force. So that is an example of work being done. Sorry. So when work is done, work, this type of energy, is transformed into kinetic energy. So if you don't see movement, work didn't happen. But just because you saw movement doesn't mean work did happen. There's some stipulations about what determines work being done. So if you lift an object, it gains gravitational potential energy, and the amount of energy it gains is equal to the amount of work done to lift that object. So let's say you lift a bowling ball over your head. The amount of work energy it took to lift that bowling ball up and put it on your head is the amount of gravitational potential energy you would have. Because remember, the law of conservation of energy says all energy is transformed from one form to another. It's never lost or created. So, the work done against gravity needs to be the same as the potential energy that the object has once it's lifted. And if you are lifting an object straight up or you are pushing it up a ramp, it's still the same amount of work. Even if one was easier than the other, you're still accomplishing the same goal. You put this object in this location, and that's the work that was done. Now, the force is something different, or the effort required to get that object where it needs to be is different than work, but it doesn't matter how you did the work is the same, even if you used a tool to help you. Oh, that was kind of convoluted. Anyway, so we can see evidence of work in the following situations. If you have a toy car and you push that toy car and it moves in the direction that you pushed it, that means work has been done. If you take a fan connected to a battery and place it in an electric circuit and it moves, then work was done on the fan. It's applying a force and then movement happening as a result of that force. When an object is lifted, it moves, work was done on that object. Now we're going to talk about how to calculate work. There is a way you can put a value on how much work was done, and there's a formula for that. So to calculate work, you do, the formula is work equals force times distance, and it will be abbreviated as W equals F times D. Two things to remember as we do these types of problems: work is measured in joules and force is measured in newtons. So let's look at this problem. If you have a crane and it uses an average force of 5,200 newtons to lift a steel beam 20 meters, how much work was done? So 5,200 newtons would go in place of the force, the F in the equation. So it would be W, sorry, I'm going to walk over here. W equals 5,200 times the distance we said was 20. And then you just solve for work. So go ahead and put that in to the end puzzle. And let's look at the next example. So now we have a mechanic who's using a hydraulic lift. He wants to raise the car to change the tires. The car has a mass of 1,200 newtons, and the car was raised 2 meters. So in our formula, we would replace the force with 1,200 newtons and the distance with 2 meters, and then we would multiply to solve how much work was done. Put your answer in the add puzzle, and then that is it.